Now we are moving on to the third colligative property, that is depression in freezing point. Depression in freezing point. Now, how are you going to define freezing point? So freezing point is the temperature at which the liquid and solid, they are in equilibrium and the two phases are going to have the same vapor pressure. Okay, so it is the temperature at which liquid and solid are in equilibrium and both the phases and the two phases have the same vapor pressure. So this is the definition for freezing point. So it is the temperature at which your liquid and solid both are going to be in equilibrium and the vapor pressure of both the phases, that is solid and liquid, are going to be the same. Okay, now what is the meaning of this word depression? Depression means either you have to lower it down or decrease it down. Okay, now if you look at the freezing point of a solvent, okay, the freezing point of a solvent is very high, so we are going to cause a decrease in the freezing point. So what are we going to add? We are going to add a non-volatile solute again. Okay, so we are going to add a non-volatile solute plus a pure solvent, which is going to form our solution. Right, now this non-volatile solute, it has, or you can say the freezing point, or the freezing point is low. For pure solvent, the freezing point is extremely high. So if you are adding a non-volatile solute to a pure solvent, what is going to happen to the solution? Because you are adding a non-volatile solute, your solution is going to get a freezing point which is lowered. Okay, so because of this, the freezing point is lowered. And what is the reason for lowering of freezing point? Addition of a non-volatile solute to the pure solvent. Okay, now let us take T0F as the freezing point of pure solvent and TF as the freezing point of solution, which is along with a non-volatile solute. So tell me which one is going to be greater. Of course, here T0F, I told you T0F is the freezing point of pure solvent, so I told you it is already high. So T0F is going to be greater than that of TF. Why is the freezing point of solution becoming low? Because you have added a non-volatile solvent. Now, how are you going to define the freezing point depression? Okay, so it is the difference between the freezing point of pure solvent and that of is called freezing point depression, or you can say depression in freezing point. And this is denoted by delta T. F. Why? Because it is the freezing point. So write delta Tf is the difference. So you have to put a minus sign. Difference between what? The freezing point of pure solvent. Pure solvent is denoted by T naught F minus to that of solution. So solution is denoted by Tf. So this is the first equation for your freezing point depression. Okay, so I hope this is clear. This is a graph which shows the variation of vapor pressure with temperature of pure solvent, solid solvent and solution. Okay, so you can see the x-axis represents the temperature, y-axis represents the vapor pressure. Altogether there are three curves here. AC is the vapor pressure temperature curve for solid solvent. Then you have the vapor pressure temperature curve for liquid solvent, which is BD. Then EF is the vapor temperature curve for the solution. You will see that the vapor pressure temperature curve for solution always lies below that of the solvent. If you look at curve AB and curve CD, they both are intersecting at point B. So you can see down there that B, it corresponds to the freezing point of the solvent. Now at point B, if they are coming together, that means their vapor pressure are going to become equal. Similarly, curve AB and curve EF, they collide at point E, or they meet at point E, and that is when the vapor pressure of that solid solvent and solution becomes equal, and that corresponds to the freezing point of the solution. Here the freezing point of solution is lower as compared to the freezing point of solvent, because it is evident here. You can see the vapor pressure temperature curve for solution lies below to that of vapor pressure temperature curve of liquid solvent. Now, why is it so that after addition of a non-volatile solute to a pure solvent, the freezing point is reduced or lowered? Now, imagine at the freezing point of a liquid solvent, the intermolecular forces of attraction, or the attractive forces between or among the molecules, they are very strong. Okay, so they have a higher tendency to change its phase, that is, it can get converted from liquid to solid phase. But when you add a non-volatile solute to that solvent, the solvent molecules which are together bind by the strong intermolecular forces of attraction, they are separated by the solute molecules. Of course, if you are adding solute, means solute molecules also mix up with the solvent to form the solution. Now hence, when this separation takes place, the intermolecular forces of attraction are broken, or they are not that strong, right? And that is why the freezing point of the solution is decreased by the addition of a non-volatile solute. Now we are going to study the freezing point depression and concentration of solute. Freezing point depression and concentration of solute. Okay, now it is found that the freezing point depression is represented by delta Tf. Okay, it is directly proportional to what? Same like your boiling point elevation. So it is directly proportional to molality of the solution, and we know that molality is denoted by small letter m. So just put this statement in equation form. So freezing point depression, so that is delta Tf, is directly proportional to molality m. I told you, if you have to remove this proportionality sign, then you have to put a constant, proportionality is constant, and an equal to sign. So it will become what? Delta Tf is equal to Km. Okay, now just don't forget to put K F here. F stands for your freezing point depression. Now this Kf, it is the proportionality constant, and the other name, and it is also called as freezing point depression constant, or you can also call it as cryoscopic constant. Okay, so there are two names for this proportionality constant. One is the freezing point depression constant and the second one is cryoscopic constant. Okay, now similarly, the way we solved for boiling point elevation, we are going to do the same derivation out here. Now if you take molality as 1, okay, so you can consider this equation as 1. So what form this equation is going to take? So it will be delta TF is equal to, if m is equal to 1, it is going to give you Kf. So now how can you describe or define this cryoscopic constant? So cryoscopic constant is the depression in freezing point produced by 1 molar solution. Okay, so only when you took m is equal to 1, you got delta TF is equal to Kf, and now we are defining Kf, that is nothing but cryoscopic constant. So cryoscopic constant is the depression in freezing point produced when you consider 1 molar of solution. Okay, now next is you need to know the units. So to find the units of Kf, you have to consider the equation, that is delta Tf is equal to Kfm. Now get this Kf on the other side, so you are left with what? Delta Tf and m. Now here the temperature is measured in terms of Kelvin and also in terms of degree Celsius. Okay, and we know that molality is mole kg inverse already, so this is going to be mole kg inverse. But I told you, you can also write it as kg. When this goes up, this inverse is going to get cancelled, and if mole is going up, of course there is nothing out here, so you have to write mole inverse. Similarly, if you want to write this, it is going to be C degree Celsius kg mole inverse. So you can write it in this way or either the other way around. Okay, so these are the two units that I use to measure the depression in freezing point. Now we are going to study the molar mass of solute from freezing point depression. Molar mass of solute from freezing point depression. Okay, now again we need to consider the same equation, that is delta Tf is equal to Kf dot m. Now if you remember, when we were deriving boiling point elevation, we had deduced the equation for molality, that m is equal to 1000 W2 upon M2 W1, right? So this value we are going to substitute here. So what you will get, delta Tf is equal to Kf dot, in place of m substitute this value, W2 upon M2 W1. Since we are very much related to molar mass of solute, we will remove this M2 out. So if you remove M2 out, what is going to happen? Kf is going to remain as it is, and then just copy down everything in the similar manner, and then this delta Tf will go down dot W1. So this is the equation with which you can calculate the molar mass of solute from freezing point depression. Now with this we finished with the third colligative property.